This video will be a serious one, and I'm gonna show you how I determine speeds of a robot. These calculations can be used for a featherweight or a beetle weight or maybe even an ant weight. First of all, I'm gonna use Microsoft Excel to do the calculations. It's my go-to tool. You can use Google Spreadsheet or OpenOffice version. Doesn't matter. And at the end of the video I'm gonna put the download link so you can download this sheet yourself and play with the calculations. Let's say you want to build a heavyweight and your main goal is to fight in the extreme robots arena. Let's draw that arena. That arena, and I checked, is not square, it's rectangle. And let's put the logo in it to make clear. And I know the total length of the arena, 12 meters high, and it's gonna be 8 meters. That's the size of the arena. So what's a fast robot? Now, if you remember the Hypershock fight, Hypershock went from one side to the other side in less than a second. And this was the BattleBots arena with what is a little bit bigger. But let's focus on arena in the UK. So 12 meters. If you cross the whole arena in 1 second, you have a really fast robot. If you cross it in 2 seconds, it's about average. If it's important to have a good control robot, maybe 3 seconds. From one side to the arena to the other side. First we have the arena length. And we know this is 12 meters. Time to cross arena. And that will be 3 seconds. We know the arena is 12 meters. We know we want to cross it in 3 seconds. And now we have a speed for a robot. Speed in meter seconds. We're gonna take the 12 meters and divide it by 3 seconds. So 4 meters second. Not a really common speed. So let's translate that to kilometers hour. We're gonna take the speed divided by 1000, multiplied by 60 seconds and multiplied by 60 minutes, and we know our robot now is 14.4 kilometer hours. I'm going to say 14.4, I don't know what that means. Well, I understand. Let's convert it to miles an hour, and that's the speed roughly multiplied by 0.6 to 1. So now we know if a robot needs to go from one side to the arena to the other side to the arena, the top speed of the robot has to be 14.4 kilometers an hour or roughly 8.9 miles an hour. And this is, we forget about wheel spin, we forget about it takes some time to get to top speed. Just say it's the perfect world, we hit full throttle and the robot just goes. Now we know the speed. How do we calculate what motors to use or what reduction on our motors or what batteries? So let's say we have a wheel. Let's put in a wheel, and this wheel needs to rotate a certain amount of times to get from this side to the arena all the way to that side of the arena. How do we figure out the amount of rotation? Well, first we start with the wheel and we want to know the diameter. Diameter of the wheel, and we call that D. In this case we're gonna say it's meters. It's not a small wheel, not too big. Let's say it's 25 centimeters or 0.25 meters. And that's this part. And if we know that part, we can calculate the circumference of the wheel, so the whole outside, and we use pi for that. It's a very simple formula. Circumference circumference is pi times diameter. Let's calculate that. Pi, if you don't know, well, you must know, otherwise you didn't pay attention in school. Pi is roughly 3.14. So is 3.14 times the diameter in meters. And now we know the outside of a wheel total length is 0.79 meters. Rotations to cross the arena. We have the length of the arena, we know that. It's 12 meters. And we divide that by the circumference of the wheel. And we know this wheel has to spin 15 times and a bit to get from this side of the arena to that side of the arena. And we want to know how many rotations per second. Let's do second first. We know we want to cross it in 3 seconds and it has to do 15 rotations in that time. So we take the amount of the rotations and divide it by 3. And we found out per second it has to do 5.95. Let's round that down. 5.10 rotations per second to get from this side to the arena all the way to this side to the arena in 3 seconds. Rotations per second. Now, motors normally use rotations per minute. So it's easy to figure out. Rotation per minute. And we know the second, so it's just, let's take that value and multiply it by 60. And we have the RPM. It's that simple. So we know our output in full throttle has to be 305 and a bit rotations per minute. Now, back to motor speed. Motors use rotations per minute. The brushless motor, like the Bosch we know from the past, they're like 3000 rotations a minute. But these days we have a lot of brushless motors, and brushless uses a value called kV. kV is the rotation per volt. So motor speed, and that's in kV RPM per volt. Let's just take a common slow motor, 120 kV. That's what we use in Petunia. And we also have lipos in Petunia. Lipo, they say S. So lipos we use a total of 10 S in the robot. So to calculate what the speed of the motor is, motor speed, to calculate it, we take the kVs, multiply it by the voltage per cell, and a lipo range varies, but the average is 3.7, and multiply that by the cell count. And now we know if our motor is given 10S and it spins at full speed, the total RPM is 4,440 rotations per minute. And that's too fast because we need 305 rotations per minute. So now we know we need a reduction. Every robot has a reduction. Reduction needed. We take the total motor speed and we divide it by the rotations per minute. And we found out we need a gear reduction of about 14.5 to 1. That's it. So let's make this a nice and pretty Excel. Okay. I want to gray out the values we don't change, so these going to be a little bit darker. And this is the input value. These are both calculated values. This is a calculated value, and this is a calculated value. So now we know, using this sheet, if things change. So let's say the arena goes bigger, but we want to keep the same speed. We see our gear reduction go down. And if we change the arena size to a smaller one, it goes up. Same for speed. If I want to go from one side to the arena in Hypershock style in 1 second to the other side, well, we need a really low gear reduction. This is important. You can't just use any gear reduction. Your motor has to have enough power for it, but we'll cover that in the next video. So that's it. Any questions, comments? Leave them down in the comment area. There is a link in the description so you can download this sheet. And well, that's it. Have a good day.